So I hope everyone has refreshed and reacquainted with where we were. So let me remind you. So what we're talking about on the road to our general study of decoherence and measurement are the foundations of how we describe open quantum system dynamics. Okay? So the general paradigm for that is to think there's some particular subsystem that we call the system whose evolution, whose dynamics we seek to follow. And there's all the other degrees of freedom which can interact with our system, which we call the environment. Okay? And so if we have such a description, if that's all there is to the universe, then the whole thing evolves according to some unitary evolution. But the subsystem, we call it the system, doesn't necessarily evolve according to a unitary map. And the way we can describe that is for a particular case where we say, let's suppose that the input here initially, the system is uncorrelated with the environment. And then the two interact. They evolve according to a general unitary map for everything. And then we trace over the environment, and that is, after that interaction, what the state of the system is alone, right? That's all the rules of quantum mechanics. And what we showed last time is that thus can be written as a kind of input-output map. The output state is some superoperator, that acts on the input and gives us the output. And with this representation, we showed that this is equivalent to a sum of what look like unitary maps, but are in fact not generally unitary maps. They're Krauss maps. Okay? So these operators M are the so-called Krauss operators, and this model that we've written, those Krauss operators are the partial matrix elements. So these states are states of the environment. And we take the partial matrix element, so what's left here is not a number, but an operator that acts on the system. Where mu here is some general basis for the environment. It need not be an orthonormal basis, by the way, although I think I said that last time. It's not necessarily the case. For example, if we're talking about modes of the field, this could be the set of coherent states, which is an overcomplete but not orthonormal basis for the system. And we'll come back to that. That will ultimately become interesting and important when we talk about continuous measurement. Okay, so this is we've had what's called a model, an ancilla model for where we think about the environment as an ancilla system to the system for our input-output map. But more generally, we could say that we want whatever our map is on the system to satisfy some physically motivated or informationally motivated properties. That map should be that the output state should be a physical state, which means that its eigenvalues better be positive. They better represent probabilities. That if my state I knew could be prepared as with some probability as rho 1 and some other probability as rho 2, so I have some convex combination of possible states, that should be the convex combination of the outputs. So the way probabilities would make sense in the system. That we showed that generally such a map will be not trace non-increasing, it will be trace preserving if all of the degrees of freedom are such that we never move to another subspace within the system. And that trace of this operator in the Krauss representation is the sum of these guys. Okay? Which, if it's trace preserving, is the identity operator. And moreover, we argued that it should be such the case that if we had some reference system, oh God, I forgot. No, it's the discarded system. If we have some other part of the universe that is out there, that the system could be entangled with or have interacted with, that to describe the particular map on the system alone, if there is a map on that system, it should be the case that if that map does nothing, does absolutely nothing to the discarded system, it only acts on the system, that this total map must be a physical state. That's the condition of what's called complete positivity. And there's a whole deep mathematical structure associated with that. And what can be shown is that every CP map, completely positive map, is equivalent to a Krauss representation. So if it has a Krauss representation, it is a CP map. If it is a CP map, it is a Krauss representation. It means there exists some ancilla state and some unitary, which when I trace over it, gives that map. Even if I don't have, in the physical circumstance, the knowledge of what that ancilla state was. It's just a mathematical relationship. Okay? Yeah.
I'm reminded a little bit about scattering theory, where you would see wave operators instead of views, mapping the initial density measurements to that. And those wave operators are partial isometries, and I'm wondering if these Krauss operators are in some sense.
Not necessarily. I don't believe so, because their columns need not be orthogonal. I believe they're not partial isometries in general. Right. Now, one last point to reemphasize here is the particular case that, suppose to give a little bit more thought to what these Krauss operators are, is if we started with our system was initially a pure state, and it evolved according to this map, written this way, then the output state is generally a convex combination of pure states. It itself is generally mixed. So even if the initial state is pure, generally the output state is mixed. And the states that occur in this ensemble decomposition are given by the action of each of the Krauss operators on whatever this state is, renormalized, because this is not a unitary, so I forgot that, got to renormalize it. Where the normalization here, the square of the norm of this vector, is the expected value of n dagger n. Okay. We'll come back. That's going to be very important when we talk about quantum trajectories, this interpretation. But one point we didn't mention last time that I just want to conclude with is the point that the Krauss operators are not unique. There it is. So what we have is that row out, there is some map that maps the output state to the input state. I'm sorry, the input state to the output state. And that map can be expressed in terms of some set of Krauss operators that conjugate the input. However, I claim that there can potentially be another set of Krauss operators which, when conjugated and summed, give exactly the same output state. Okay? So the set of Krauss operators that define the input-output map are not unique. How do we see that? Well, there's many ways to see that. One way to see that is to look at the following. Let's just look at this particular case where the input state were pure. Although this is generally the case, it's not restricted to the case that the input state were pure, but let's just look at that as a specific example. So what we have here is that the output state is itself a statistical mixture. However, we know that the ensemble, there are an infinite number of ensemble decompositions which give the same density operator. As I emphasized last time, this is not necessarily the diagonal representation. These are not the eigenvectors of the density operator. This is just some particular statistical mixture. These psi mu's need not be orthogonal to one another and generally will not be. So there's a whole nother set of potential pure states which, when taken in convex combination, weighted by some other set of probabilities, gives the same density matrix. We know that, right, from our studies from last semester. The ensemble decomposition is not unique. What is the condition on these ensemble decompositions that, in fact, they're equal? Well, what's required for them to be equal is that they're related by what's so-called unitary remixing. So for example, if I come back over here, I can say, suppose I write mu as a sum over nu, some matrix mu nu and nu, where the columns are orthogonal. Then when I plug this into this and sum over mu, I get that. Because of the fact that these are columns of an orthogonal matrix. I didn't say this is necessarily a unitary matrix because this comes to your point also. This could be a partial isometry in the sense that the number of Krauss operators in the two sets need not be the same. I could have 2 Krauss operators here and 3 Krauss operators there. They need not be the same number. This should be mu, sorry, mu max. these need not be the same. All that's important is that the columns of this be orthogonal. And that's called a unitary remixing. Another way to look at it is the following. When we derived the map based on this model, we chose an arbitrary basis in which to do our trace over the environment. We could choose any basis we like. And that basis can be overcomplete. It need not be orthogonal. As we know, we can take the trace, for example, for coherent states, we can use a resolution of that identity over a continuum. And then I'd have a continuum of Krauss operators. That'll be fun. Or I could have something that's finite, but overcomplete. So as long as I can define the trace class, I can choose any basis I like to take this trace, and I'll get a different set of Krauss operators, as long as there is a way to transform from one basis to another. The point of this is that in this open system dynamics picture, the system is coupled to the environment, but we're tracing over the environment. We're not looking at the environment. And because we're not looking over the environment, it doesn't matter what set of states we use in order to analyze the dynamics of the system alone. Now, it might be interesting to say, hey, what would happen if I actually looked at the environment? And how would that affect the system? Well, then we'll have, that's going to be an interesting thing to think about. Because then the different Krauss representations will represent different possible measurements that I could do on the environment, which would then affect the system differently. However, if I sum over all possible measurements that I do over the environment, well, then I better get the same thing. That's a little bit of a foreshadowing of the theory of quantum trajectories. Yes, sir.
So, so initial state can go to the final state in any possible trajectories, right? I mean, depending on, so since there is no unique Krauss operator, so it can take any trajectory, I mean, any type of.
I'm not sure you mean by any. They must be related in this way. And what is true is that this is unique. So this relation, the relationship between the input and the output is unique. And it's defined by the nature of the interaction that occurred. It's the physics that occurred defines how the system evolves when it's in contact with the environment. What is not unique is how that particular input-output map is decomposed into a set of these conjugated type interactions. Once I sum over mu or sum over nu, I get the same thing. Because we're not keeping track of what's going on to the environment.
So the question is that, is there any preferred set of Krauss operator which will be preferred when the system goes from input state to output state?
No. No, what I'm saying is that this equals this, no matter what, as long as these guys are related this way. There's no preferred set of Krauss operators that defines the map. They're equal mathematically, period. What is a different story is if I don't do this kind of dynamics where I trace over the environment, but instead look at the dynamics of the system conditioned on some particular measurement of the environment. If I actually look at the environment and ask, how does the system update conditioned on what the environment, what I saw in the environment, well, then there is a preferred set. But if I then sum over all possible measurement outcomes, well, then it's independent of the particular measurement I did. All right. So now this is a fairly abstract, and it can become much more abstract, really get into the guts of this, mathematical description of input and output. There's not a lot of physics here, and I want to put the physics in now. To get started on that, I want to think about the following. So let's just think about, let's compare what we know from our standard quantum mechanics. When we talk about dynamics, for closed system dynamics, we say, okay, there's some unitary evolution. There's a unitary map, which says maps me from what the system is at time t1 to some later time t2, such that the evolution generally of whatever the state, if it's evolving unitarily, is such, right? However, what's interesting, where the physics in here is the generator of time translation. What is that? Well, what is that? That's to say, if I want to know for a small differential time dt, what is the state of the system at a later time, right? So that's the unitary evolution that displaces me by a small dt. Then what we know is that the generator of these times translation is the Hamiltonian. That's where the physics at. So we say that the generator of time translation is what we call the Hamiltonian. And we give it, so that's where h bar comes into the story. So this is where all the physics is at. This is the Hamiltonian. It's the generator of time translation. Okay. So that we have according to this, if I keep terms up in the standard calculus up to order dt, the state of the system that evolved according to this unitary evolution at time t plus dt, plugging in this, is equal to, well, I'll just write it out. So that's rho minus I over h bar ht minus rho h dt plus order dt squared, which we neglect in calculus. Okay? So what we see here is we get the Schrodinger equation. That written here in terms of the density operator, but it's still the Schrodinger equation, which says that the time evolution of the density operator is given by the commutator of h with rho. Or I can write that as a kind of map minus I h bar, the add operator in the Lie bracket sense acting on rho t, where add A on B is the commutator of A with B. I want it to be fancy. Okay, so that's familiar at some level, right? And of course, the physics is all about what the Hamiltonian is and how we can control it and define the dynamics, in this case, unitary dynamics. Our goal now is to say, what is the equivalent form for the open quantum system dynamics? What is the generator of open quantum system dynamics? So not in the open system dynamics case, we had that, we could look at this now, input-output, as a time-dependent thing. The state at time t is some map which, well, I'll write it in a kind of similar way. So this is a CP map. That's the open quantum system dynamics version of this. So we have the state at time t1 of the system. This is a map on the system that takes it from the input state at time t1 to the output state at time t2, where t2 is greater than t1. Okay? So what is the generator of that map? In the sense that if I wanted to ask, given the state at time t, what is the state at time t plus dt? Okay. Well, that's actually a hard problem, generally speaking. What we're going to look for is maps that are of the following form. Similar to this, so they take the state at time t to the state at time dt, acting on the state at time t. So we seek this. Not, as we will see, not all physical open quantum system dynamics are of this form. This is a very special case. Because what we see, as we'll show in some detail as the lecture proceeds, the map generally doesn't just act on the state of the system at time t, but depends on the whole history between t and dt. Written in this form, this is what's known as the Markov form. So we're going to assume the Markov form to start. We're going to assume that the map has this form, that is to say that the state at time t plus dt is a map acting on the state at time t. And then given this assumed form, figure out what the Krauss representation of this has to be, just from the basic properties we described. Given that, we'll then try to derive that from basic principles. Okay, that's where we're headed. Yeah.
This is maybe a silly question, but so you said that only some maps satisfy this bottom.
Yeah.
Why is that different from the top equation? Because all maps, all physical maps can be written like that, right?
Let me see. The difference has to do with the differential form. I guess what's wrong about this is this. This doesn't just depend on that. That's not a general form.
Okay.
This is a general form of, it's a map from the input to the output, but it doesn't just depend on the endpoints. It depends on the whole history.
I see.
But this is a very particular map.
Okay.
It only depends on the endpoints. So if we assume this in this Markov form, let's take a look at this more carefully. Well, this, we know if it's a CP map, can be written in terms of a set of Krauss operators. All right, so let's see. Right. Whatever this is has to be of a similar form to what we have over here. That's to say, the state at time t plus dt can be written as this plus some operator dt plus order dt squared. Let me just finish this one. So now the question is, what form must the Krauss operators take in order to achieve this kind of differential map? Well, we can see that. Let me go over here because I don't want to write this out yet.
The second Krauss operator is a dagger.
Indeed. Thank you. So what do we have? Well, firstly, we can write if this is going to be of this form, there are terms that are of this sort. Right? Because those terms, if I look at their conjugation, form L mu rho L mu dagger dt. So that's perfectly good. So if I had Krauss operators of that form, they fit this. However, that's not all we could have. I can also have an operator M0, which is similar to what we had here, which is the identity plus something which I'll call G dt. That's another perfectly good Krauss operator, which would fit this, right? And because M0 rho M0 dagger is rho plus G rho plus rho G dagger dt plus order dt squared. So all of that is perfectly good. In fact, that's all we could possibly have. These are all the possible forms of the Krauss operators. Yeah?
The second argument on the top line in the n hat, should that be dt? The second argument of the
Oh, that should be a T.
yeah, and the line above it.
Yeah, thank you. So, just based on the fact that we assumed this Markov form, which says that the map that takes me from t to dt acts only on the state at time t, and that fact that that's describable by a Krauss representation gives us this form of the Krauss operators. Moreover, if the map is trace preserving, so let's look at that specific case. Then we know that what that means is that the sum over Krauss operators is the identity. That's what we had in the beginnings of the course. So let's say what that is. Well, that's equal to M0 dagger M0. So this is U to sum U max. Plus the sum U equals 1 to mu max and mu dagger and mu. So let's plug that in. That's equal to the identity plus G dagger dt plus order dt squared, which we drop. So that's that term. Plus sum over mu L mu dagger L mu dt has to equal the identity if it's trace preserved. So this condition thus gives us a relationship between these operators I called G and the operators I called L. What it tells us is that G plus G dagger has to equal minus the sum over mu of L mu dagger L mu. That is to say, the imaginary part of G can be anything we like. The anti-Hermitian part of G can be anything we like. But the real part of G, the Hermitian part of G, has to be equal to half of this. So that means I can write G as some Hermitian operator K and some anti-Hermitian operator. So I'll factor out the I, and I'll put a minus sign because guess what? I'll call that the Hamiltonian. And K has to equal half of this. So it's equal to minus I H, the Hamiltonian, minus a half, sum over mu, L mu dagger, L mu. So just from the fact that this is a physical CP map in the Markov form gives us the following. Rho of t plus dt is equal to m0 rho m0 dagger plus sum over mu mu dagger, I'm sorry, mu rho mu dagger, and plugging that in, that is equal to 1 minus I, oh, by the way, I'm going to call this, let's define H effective as H minus I H bar over 2 L mu dagger. Then this is equal to minus I over H bar H effective. H effective is not a Hermitian Hamiltonian. It has a Hermitian part, which is the Hamiltonian, and an anti-Hermitian part, which is this. Come back to the physical interpretation of that in a moment. So what do we got? We got minus I H effective dt rho 1 plus I over H bar H effective dagger dt plus sum over mu L mu rho L mu dagger dt. Isn't that interesting? It may be starting to gel into something we've seen before last semester. What we see here is then, if I multiply this out the same way we did before, take the ratio of this minus the identity divided by dt is equal to minus I over H bar, H effective rho, minus rho H effective dagger, plus sum over mu L mu rho L mu dagger, all for the system. And everything here is a function of, can be a function of time. Finally, I'll write this out, write out the H effective because both forms are useful. This is equal to minus I over H bar, the true Hamiltonian H, commuted with rho, plus minus a half, I'm sorry, plus sum over mu minus a half L mu dagger L mu rho minus a half rho L mu dagger L mu plus L mu rho L mu dagger. step back from that for a moment and analyze it. This form of the evolution is the generalization of Schrodinger's equation for open quantum system dynamics. This is known as the master equation in Lindblad form. We've seen it. We've seen it last semester when we did this in a somewhat phenomenological way, where we added an imaginary part to the Hamiltonian to take into account the fact that there was a finite lifetime and spontaneous decay. And then in order to preserve population, we had added terms that we did by hand that we call the refeeding terms. This is the form we saw before. We see how it is derivable from the principles of just assuming that there exists a map of the form that we said before. And I'll just write this as dt. So assume that everything is time, the Hamiltonian and the L's are time independent, then it would be of this form. Yes. Assuming we had a map of this form, and assuming it was a CP map, this is the differential equation. We have the Hamiltonian, that's good. But we have these new things, these L's. The set of L's, there's so many definitions. We have the Krauss operators. Now we have these other things. They were kind of like the Krauss operators and these DTs. These are called the Lindblad operators. Sometimes known as the jump operators, and that'll become clear later. And what Lindblad proved was that the only differential equation whose integral was a CP map had to be of this form. It was a Markov equation. That's what he proved. We're going to see this now for the rest of the semester. The master equation in the Lindblad form.
Yeah. Seems to me that you have made some assumptions implicitly about what happens when dt is 0. In other words, zero, mu equals 0 is sort of an initial state, if you want, and because the m mu t plus dt t, when you put dt goes to 0, then you got m mu of t and t, and that's going to be 0 unless there's something very singular going on. So you're assuming something about how the time evolution is starting.
Let's see. So what we are assuming is that as dt goes to 0, that this is the identity map in the same way as this. This is important. I mean, it's really a generalization of this. So we have a near identity map. When
But
dt
you're
goes 0.
assuming that the identity is focused in one value of mu.
That's right. So I chose that particular one to be the case. In order for, in principle, as we say, we can do a unitary remixing. The Krauss operators are not unique. And I can mix them together, and we will. But this is a Krauss representation, which satisfies the conditions that I wanted to satisfy, which is that when dt goes to 0, this is the identity map. And that I'm keeping no Krauss operators such that the conjugation gives me anything higher than order dt. So
this form is correct. It's not okay. If you started out with some Krauss operators that were mixed in a different way, then you could transform them so that you would be starting the way that you need.
So what we'll see is that we'll always have a Lindblad form, but the Lindblad operators are not unique. So I can, by doing a unitary remixing between M0 and M mu, I'll get the same master equation, but with a completely different set of Lindblad operators. We'll come to that in a little bit. In a little while. Yeah.
This is kind of jumping on Charlie's question from earlier.
Uh-huh.
But in the case that, sorry Charlie, in the case that the Markov approximation breaks down, but you still have, continuous trace preserving time evolution, do you know what way that form would get changed?
Yeah, well, that's what we're about to do.
Oh, okay. Cool.
So what I proved was that if I can write my evolution in the Markov form, then I end up with a Lindblad form of the master equation. What I haven't told you is, what are these Lindblad operators? I wrote them just generally, but I don't know what they are in terms of actual physics. So what we want to do now for the remainder of the lecture and into Thursday is try to derive this now from first principles, from a unitary evolution of the whole thing, and see where the Markov approximation comes in and what's the more general form that doesn't have the Markov form. And maybe that will clarify the question, which I didn't clearly answer earlier. But let's get to it, and we'll see where it came in. So how do we do that? We want to derive the master equation now, not from just the general theory of CP maps, but from the particular physics that describes the interaction of a system and an environment. Okay? So what we want to do is derive the master equation from first principles. I didn't derive anything. All I did is I assumed it had a particular form, and then it, under that assumption, saw what the differential equation had to be. But I didn't derive this form. I just assumed it was there. So now let's derive it, because it's only approximate. We know it has to be approximate, because this is an irreversible evolution of the state. And there's no exact derivation of irreversibility. We have to, the rabbit went in the hat somewhere. Let's see how. So I'm going to look at the following scenario. We have the environment, and we have the system. The whole thing is described by some Hamiltonian for the system plus the environment. There is some Hamiltonian for the system, there is some Hamiltonian for the environment, and there's some interaction Hamiltonian between them. Okay? Without loss of generality, I'll take these to be time independent. Okay, there's no classical modulation. We could put that in, but it doesn't change anything fundamentally. So the system environment state evolves according to the Schrödinger equation. Let's go to the interaction picture, because what we're going to do is something analogous to what we studied last semester when we studied the spontaneous decay of an atom into the vacuum. That problem we studied last semester, we did that using the Wigner-Weishaupt theory. You remember that? Maybe. You should go back and review it. It's a good idea to do that. And you remember that was basically, the Wigner-Weishaupt theory was a kind of second-order perturbation theory. It was based on second-order time-dependent perturbation theory. And when you do time-dependent perturbation theory, it's convenient to work in the interaction picture. Okay? And in the interaction picture, the state evolves according to the interaction Hamiltonian, where all the operators evolve according to the free evolution. So I'll write down the Schrodinger equation in the interaction picture, where now everything's in the interaction picture. Fine. So now what we're interested in, though, is that we want to know what is the evolution of the system alone, which is the trace over the environment of the joint evolution, which is equal to the trace over the environment of the commutator of the interaction Now we can already see here that this is not of the form some, I don't know what I want to call it, some L as a function of t acting on the system alone. It's not of that form, because this is the system environment coupled evolution as a function of time. I can't just bring the trace inside here, because the interaction Hamiltonian depends on the interaction between the system and the environment. In fact, if I could just integrate it, and you can see that. So the system at t plus delta t, the system environment coupled evolution, is that minus the integral from t to t plus delta t dt prime 1 over h bar, h interaction at t prime, system environment at t prime. If I trace over the environment, well, this depends on the whole history. I can't write this as something that just depends on the system at time t. It depends on the whole integral from t to dt. Why is that? Well, it's easy to understand why that is if I come back to this picture, because generally what happens to the system at a later time doesn't just depend on what the system is at that time, but at time t1, information travels from the system to the environment. And in principle, at some later time, what happened there comes back to the system. So what happened, the evolution of the system at time t depends on the whole history, in principle. If I'm just looking at one subsystem. It doesn't depend on, it depends of course on the joint state at the local time, right? That's written here. What happens to the joint state at time t depends locally on what the joint state is at time t. But if I want to know just what happens to one part of that at time t, I can't just look at that one part at time t. I have to know its whole history of what happened. So that's where the Markov approximation has got to come in. We've got to somehow, if we're going to get irreversibility out of our system, we have to somehow throw away this correlation. Otherwise, the whole thing is in principle reversible. And we would have the Schrodinger equation.
So the equation that you wrote on the second line is wrong?
No, it's correct.
Ah,
It's totally correct, but it's not a function
oh, okay.
of rho of the system at time t alone.
Okay. That should be a dt. Or delta t.
Delta t, indeed. Yes. That's the point. So where we want to go with this then is to look at some approximate solutions that are justifiably good approximations. That's the art of physics, is doing good approximations. All right, let me get my notes out here. And, all right. Oh dear. The one is shuttling along at a snail's pace. Now, we can see, we can get an approximate solution to this if we can, in some way, coarse grain over the detailed dynamics of what goes on between the system and the environment. If we try to keep track of all the details of what happens between the system and environment, well then that's a reversible, the whole reversible unitary evolution. But in some way, what we want to do is ignore some of the small details that happen in terms of the correlation between the system and environment and keep the coarse evolution. How do I justify that? Well, we can justify that in a classical picture. Let's imagine the following scenario. Let's think about a classical picture of a system and environment. Suppose here's a lake, okay? And I've got a very hot penny. Ow. Put a little Bunsen burner, and I throw it in the lake. Okay, here's my penny. Now this is at some temperature T. And what's going to happen? Well, eventually it's going to come to equilibrium. How does it come to equilibrium? Well, what's happening, of course, is that molecules are bouncing off of this penny. Those molecules have some particular temperature. They have some distribution of momentum. And for some short time scale, the trajectory they take depends on the penny. The molecule of water is correlated with the state of the penny. But very, very quickly, it's going to run into other molecules that are moving around randomly. And this molecule is going to come back to thermal equilibrium. And is going to forget about the correlation that it had with the penny. Now, of course, that's not exactly true, right? Because, in principle, the whole thing is a closed system. But to the degree to which we coarse grain and throw away that information is the degree to which we can get irreversibility. The degree to which we lose information about how this particular molecule bounced off of this penny and treat it as just one member of the whole ensemble that's back at thermal equilibrium. Now, an important thing to keep in mind here is that there are two very different time scales. Back to time scales. Here we are. We have a time scale tau c, which I'm going to call the correlation time. This is the time scale over which there is, in principle, I can reverse this molecule and bring it back to where it was because I know exactly how it is. But after some very short time, it's getting bombarded by all these other random molecules, and it loses memory of that particular trajectory. That time scale is a time scale over which this molecule is then rethermalized. With the rest of the lake. And I can't tell which molecule that was. There's another time scale, which is the decay time. So there is eventually, this hot penny is going to come to thermal equilibrium at temperature T. That time scale was going to require a bombardment of a lot more molecules. Any one particular molecule or some small collection of molecules is not going to instantaneously bring this hot penny to the same temperature as the lake. And generally, this is huge compared to the correlation time. So this thing will instantly rethermalize compared to the long time scale over which the penny comes back to equilibrium. So the way in which we deal with this kind of non-equilibrium dynamics by which a hot penny comes to thermal equilibrium and eventually doesn't get hot again, although in principle it could, in principle, all the hot molecules that were out there could reassemble themselves and bring all their energy back and make this thing hot again, but we know that in the same way when glass shatters on the floor, in principle, all the vibrations in the world could come back and reassemble it. It just doesn't happen because of the too many degrees of freedom for that to happen. So what we do in order to treat that dynamics is that we coarse grain. We coarse grain over a time scale delta t, where delta t is huge compared to the time scale of correlations, but tiny compared to the decay time. And there's enough room, as we'll see in a particular physical example of, say, spontaneous emission of an atom, where we can simultaneously satisfy these inequalities. By doing this, we are throwing away information about the correlations. Okay, so we're going to, within the time scale that's short compared to the correlation time, everything is reversible. And in principle, we can move the molecule back to where it was. We know where it is. Over time scales long compared to that correlation time, these molecules are completely rethermalized. And we've lost that information. And that's how we're going to be able to get to an irreversible equation. All right. Let me, I think I won't start that calculation, but just to say the following. I've described this in terms of a classical picture of trajectories of molecules and ping pong balls. But the same exact physics applies here, except that in principle, my environment need not be a thermal state. It could be the vacuum. And those correlations then are, instead of being classical correlations, represent entanglement between the degrees of freedom of the environment and of the system, which again are entangled for some short period of time, and then at the end of the day, I lose memory, and that whatever those correlations were lead to increased entropy of the system. So that's where we're headed, and I think we'll pick that up next time. All right, so I hope everyone has refreshed and reacquainted with where we were. So let me remind you. So what we're talking about on the road to our general study of decoherence and measurement are the foundations of how we describe open quantum system dynamics. Okay? So the general paradigm for that is to think there's some particular subsystem that we call the system, that whose evolution, whose dynamics we seek to follow. And there's all the other degrees of freedom which can interact with our system, which we call the environment. Okay? And so if we have such a description, if that's all there is to the universe, then the whole thing evolves according to some unitary evolution. But the subsystem, if we call it the system, doesn't necessarily evolve according to a unitary map. And the way we can describe that is for a particular case where we say, let's suppose that the input here initially, nothing, does absolutely nothing to the discarded system, it only acts on the system, that this total map must be a physical state. That's the condition of what's called complete positivity. And there's a whole deep mathematical structure associated with that. And what can be shown is that every CP map, completely positive map, is equivalent to a Krauss representation. So if it has a Krauss representation, it is a CP map. If it is a CP map, it is a Krauss representation. It means there exists some ancilla state and some unitary, which when I trace over it, gives that map. Even if I don't have, in the physical circumstance, the knowledge of what that ancilla state was. It's just a mathematical relationship. Okay? Yeah.
I'm reminded a little bit about scattering theory, where you would see wave operators instead of views, mapping the initial density measurements to that. And those wave operators are partial isometries, and I'm wondering if these Krauss operators are in some sense.
Not necessarily. I don't believe so, because their columns need not be orthogonal. I don't, so I believe they're not partial isometries in general. Right. Now, one last point on, and some other probabilities row 2, so I have some convex combination of possible states, that should be the convex combination of the outputs. So in a way, probabilities would make sense in the system. That we showed that generally such a map will be not trace non-increasing, it will be trace preserving if all of the degrees of freedom are such that we never move to another subspace within the system. And that trace of this operator in the Krauss representation is the sum of these guys. Okay? Which, if it's trace preserving, is the identity operator. And moreover, we argued that it should be such the case that if we had some reference system, oh God, I forgot. No, it's the discarded system. If we have some other part of the universe that is out there, that the system could be entangled with or have interacted with, that to describe the particular map on the system alone, if there is a map on that system, it should be the case that if that map does not matrix element, so what's left here is not a number, but an operator that acts on the system. Where mu here is some general basis for the environment. It need not be an orthonormal basis, by the way, although I think I said that last time. It's not necessarily the case. For example, if we're talking about modes of the field, this could be the set of coherent states, which is an overcomplete but not orthonormal basis for the system. And we'll come back to that. That will ultimately become interesting and important when we talk about continuous measurement. Okay, so this is we've had what's called a model, an ancilla model for, where we think about the environment as an ancilla system to the system for our input-output map. But more generally, we could say that we want whatever our map is on the system to satisfy some physically motivated or informationally motivated properties. That map should be that the output state should be a physical state, which means that its eigenvalues better be positive. They better represent probabilities. That if my state I knew could be prepared as, with some probability as rho 1, the system is uncorrelated with the environment. And then the two interact. They evolve according to a general unitary map for everything. And then we trace over the environment, and that is, after that interaction, what the state of the system is alone, right? That's all the rules of quantum mechanics. And what we showed last time is that thus can be written as a kind of input-output map. The output state is some superoperator, that acts on the input and gives us the output. And with this representation, we showed that this is equivalent to a sum of what look like unitary maps, but are in fact not generally unitary maps. They're Krauss maps. Okay? So these operators M are the so-called Krauss operators, and this model that we've written, those Krauss operators are the partial matrix elements. So these states are states of the environment. And we take the partial